Welcome everybody to this talk. I will try to compress a bit to catch up with the time. I don't want to keep you from the coffee break, but hopefully you will forget about it if this is interesting enough. So my name is Rafael, and I will be together with my colleague Federico. We will be presenting this talk about fault injection and combined attacks. We called it Divide and Conquer Revisited, because we will not talk too much about fault injection. We're going to actually talk about software exploits. So we're talking about software, not so much hardware, but you will see how these worlds meet together. So in this presentation, we will walk you through our message of the presentation through some case study. So here, we try to pray to demo gods, and we have some setup here. We will show what it is, we will talk about it, and we will talk about how we did an attack that was reported, and then also how it's patched, and what can you do. Let's start. So the case study, we have a microcontroller. So this is one of the newest microcontrollers. In this case, it's from ST. It's the STM32WE55. So this microcontroller, it's an IoT chip which has a ton of features. It does almost everything. So it's dual core. It has a Cortex M4 for general purpose operations, but it also has a Cortex M0 chip, which is in charge of all the wireless communications like Wi-Fi, Bluetooth, and whatnot, but also is in charge of the security domain. So this chip has two partitions, security domain and the general purpose. Important, interesting, this chip has something that we will refer to several times. It's called these option bytes. It's stored in flash, and it defines a bit of the properties of the chip. So when we looked at this chip, basically we had some research goals, and our research basically targeted typical goals. What do we want to do with this chip? So in this case, we actually wanted to set ourselves in the most realistic scenario, which is we get a device off the shelf from production, fully locked. Like nothing readable, nothing debuggable. What can we do with it? So here we had the typical assets that you might have. For example, for the secure core, we would target the runtime control, debug privileges. Can we run arbitrary code there? Also, we have secret keys like AES crypto and whatnot. Can we dump the AES secret keys? Can we dump the secure area? Maybe the wireless firmware? The same also for the non-secure core. So can we dump the contents of that thing? Or this debug lockout? Maybe I just want to copy the devices. I just want to steal the intellectual property. So can we bypass this debug lockout? In this case, we just follow the typical approach to reverse engineer embedded systems. So this process, actually you have maybe seen from previous presentation from my colleagues at Riskier. So first we want to understand the target. How does this work? Then we would try to look for issues, vulnerabilities, and eventually if we find something, we can try to exploit it. Okay? So first things first, to understand the target, we need to have something. And that something usually means the firmware, and datasheets, basically everything available to the general public. Let's start. So we took the datasheets of this device. And then from the chip datasheet, what you would see is that the readout protection, it has three settings. The RTP, or readout protection levels, they can be level 0, which is denoted by this option byte AA. And that means full access. You can read, write, debug, basically developer sample. The other extreme, RTP2, it's denoted by this flag CC in the option byte. This means you have 0 access. So JTAG access is disabled, you cannot debug anything, and on top of that, it's an irreversible state. If you ever transition a chip to that, you cannot go back. There is just, basically everything is locked and you cannot go back. Then there is the third state, RTP1, which is basically denoted by not AA or not CC in this option byte. And this is a partially locked state. So in this state, you cannot debug stuff, but the debug setting is open. Okay, so you can connect a debugger, you can debug part of the RAM and some registers, but you cannot read the flash, or you cannot do single stepping to start stepping instruction by instruction. Okay. If you want, this is a reversible state. You could transition back to fully debug, but doing so erases the chip. Okay, so this might be interesting in some production modes. Interesting to know that the secure core, the M0, it is always blocked. You cannot debug it, even if you're in the full access. The security core, security domain is actually locked. You cannot see anything. Okay, we keep reading. Then we see that the SRAM and the flash of this microcontroller, they are partitioned. And the M0 can see everything, but the M4, the non-secure core, can only see the non-secure domain. We cannot touch at all the M0 resources. This is in a way similar like TEE concepts, that we cannot see the secure domain. Also, the secure core, the firmware, the code execution, this is only reserved to ST. If you download updates for that, or if you try to find code there, the images are encrypted and signed. So we don't really see the binaries. We don't really know what is running there, other than some API functions. Okay? If you want to update, this is done through some programmer tool that you load in the non-secure core, you would put this firmware, and then the secure core does the things, but you don't see anything. A bit more details about the M0, the security domain. Security can be configured through these option bytes that we mentioned. Okay, so in production modes, you would just have everything locked down. And the M0 is something that is only written by the M0 domain. In other words, you can never touch the security option bytes of the secure domain. This is not available to people. Then most code in this secure core does wireless stuff, but it also does some things which are critical to security. For example, secure key storage. If as a user you want to use this security enclave, let's call it like that, then you can install keys or ask even keys to be installed, and from this non-secure world you can use it. You can say, I want to use key slot 3. The secure core will load the key from key slot 3, and then the non-secure world can use it, but doesn't see the key at all. Okay. So this was the code. Then basically what we wanted is, okay, let's look at what is running in this chip. For this, we wanted to look at the boot ROM. And according to the datasheet, the boot ROM is mapped at an address 1FFF0000. So we did a super complicated attack, which basically means you plug the debugger, you say, can I read address 1FF0000? And yes, sure. Okay, so you can dump the boot ROM, and then, yeah, you get the code. I'm not going to show it, but if you have one of these devices, just plug a debugger and you can dump it. So, cool. Okay, we have now some more stuff. So we connected debugger, we see it, and a quick analysis actually was very interesting because what we saw in the code actually mapped almost one-to-one what the public documentation says. Okay, so the behavior seems to match the public documentation. There is no hidden functionality, no magical stuff, backdoor, secret, whatnot. And also there were no obvious software flaws. It was very simple code, but simple sometimes means secure. And something interesting here is that there is no check actually for these readout protection bytes. So if you look at the room, then this is not there. So this means that probably this happens in hardware. You don't even see it in the software part. So the boot ROM here from attack point of view then looks very simple, but quite robust. So nothing to do here. Nice. So we look at the boot ROM, we look at the datasheets. Let's also try to do a bit more analysis on the secure core. So from the secure core, what we try to do is let's interact from the non-secure domain to the secure domain. And basically we cannot access anything. We try the classical things. Let's try to access through a peripheral, decrypt the memory from the secure core. No. Let's try connect the debugger and let's try to do something. Nope. So basically, it's actually quite decent. You cannot really interact from non-secure world with secure world. Nice. The way to interact, the way to say, for example, to wireless, I want to send something, it's via a mailbox. You have some interface where you put there, I want to write a message or I want to do some activity. Secure code will see this and then starts doing its own stuff. Very much like TEEs. The wireless stack is also executed by this core. So this was like, wireless stack, lots of code, bugs, fun. But we don't have the firmware. And the frameworks are encrypted. So we don't have nothing to work with, no reverse engineering possible, no debug access. Security domain is all isolated. So when we collect our thoughts, this is like a challenge. Fully locked device. I don't have any knowledge of the binaries that are running there. We just know a bit of the functionality. Challenge accepted. Let's try to do something. So, next step. Once we have this, what can we do? How can we identify vulnerabilities? Okay? So let's see our options. We want to do a software exploit. This talk was about software exploits and how do we do it? For a software exploit, to run some exploits, you need three properties in general. we will need to have some runtime control, some ways of doing this or diverting to this. But in this case, we don't want to do blind exploitation. So this M core, the M0 core is hidden to us. We don't know what's going on there. Usually also, if we want to do a simple exploit, we need to have a place to put this code. But the M core cannot modify the M4 memory. And the chip also is going to be locked. So even if I try to do something with the secure core, it doesn't work. But even if I try to do also with the non-secure core, it's locked. I cannot do really anything. Nice. Third, we need something that can execute code. Okay, so in this case, the flash memory is executable. But if we want to interact across cores, or if we want to full compromise the chip, we can only have this mailbox interface. This is the only part that it has shared instructions. Okay, so approaches. How can we go about this? We can go the full software approach. Okay, so we call it like fuzzing, return-oriented programming, blind exploits. This is no secret for me. This is a challenge in this setting, but okay, let's think that we would like to go this way. So a typical approach would be wireless stack, lots of code. Let's try to find something there. And if you are Jedi Master level on software exploitation, then you might think, blind exploitation, we found something here, and then we just do it. Good. Federico and I were a bit more lazy, and we just wanted to try something simple. So the longer way might be, let's try to find some leakage of information through some vulnerability. Let's try to reverse engineer a bit the behavior. Once we see what is going on, let's try to craft some exploit chain to run some code. And then we trigger the whole process, and we hope that it goes kaboom. Profit? Well, might be, but as you can see, this is not a simple thing. We, at Riskier, we try usually a lot of FI things. So we can also think of, okay, let's FI, let's glitch our way. And if you glitch your way through everything, in this setting, first, we will need to glitch this readout protection level in order to unlock the chip and at least put some data on top of it. Okay. And if we want to put data, what do we want to do? Maybe a classical glitching way for glitching code would be we load some exploit code, we load pointers to this code, and then we start glitching. Praying that these pointers, they get corrupted into the program counter of the machine, and then what we do is we jump to our payload. Okay, so you just played some code, you just put some pointers, you start glitching, and you hope that this pointer ends up as the current address. You jump to your code, kaboom. This actually, you have a paper there that, it was from some years ago, but it's very interesting if you have ARM 32-bit architectures, because it's a very powerful attack. Maybe profit, maybe not. So these were the scenarios, and then we will see how to go about this. Then, okay. So let's talk about glitching briefly before starting to explain the attack and how this works. About fault injection, you have had several talks that talk about it, but from a software point of view, if I try to describe glitching to software developers, a glitch is basically something that usually leads to some data or control flow corruption. Okay? Typically can be triggered by physical faults. Nowadays, this can also be triggered by software means under certain conditions. So for example, there is this beautiful attack, Thunderbolt, if you want to later ask Alisa how it works. Great. It's super cool, but glitching, from a software point of view, you can think of it initially as physical fuzzing. Okay, maybe if you are as old as me, like the old Nintendo video games, they had these cartridges that when you plug it and it was a bit dirty or shaky, then you start to get garbage data on the screen. It's something like that. When the software has something corrupted, it sometimes works, but a bit funky. Okay, so when we have glitching, as a developer, as a software exploiter, what does it do for me? So the first thing about glitching is fault injection. It can corrupt almost any data value. For example, you can corrupt things like registers in the CPU. And if you corrupt their program counter, then you get suddenly arbitrary runtime, not address, but arbitrary jumping to a position you might control or not. You can also try to glitch configuration registers. And if this is, for example, a copy of the OTP, the security configuration of a chip, you can unlock things, you can skip secure boots, you can mess up configuration of TE environments, so a lot of stuff. But not only these two examples. So this happens in registers, but also in on-flight data when you're doing memory copies, transfers, also in different technologies, memory which is volatile, non-volatile memory. So it happens in all sorts of places. Okay, so don't think that it's just some part. It can happen sort of anywhere. Even further, fault injection glitches the hardware itself. So this is one step below software abstraction. Actually, I have a bit of a background in hardware, so I sometimes would express that software is just a hardware configuration. So it's an abstraction. Basically, it's just the hardware does what the software tells, but it's just everything hardware. It's a physical means when you have a machine. So with glitching, we can trigger also things which are unreachable by software. Okay? This is what we sometimes call the magical behavior unicorns, like instruction skipping, instruction corruption, creating new instructions because you glitch the logic, some transistors become metastable or blow up, and then you have, instead of an other, you have something that does half an other and adds +3. I don't know. So given the proper conditions, glitching, from a software point of view, can introduce software vulnerabilities, can do a lot of interesting things. So with this context, now, how can we exploit this? If we try a classical approach, a pure approach, then we will have several issues. If we glitch our way through everything, the approach, as we described, requires 2 glitches. And we are also implicitly assuming that the device is glitchable. What if it isn't? What if, for example, I tried these glitching things into the program counter of the M0 and it doesn't work? Then it would be tricky to get the M0 to jump to my code. The other extreme, software exploiting only. You know how to do fuzzing, rope, and blind exploits. However, the chip will be fully locked. We cannot do anything with it other than just using it, whatever is there. Also, the attack path only works if there are vulnerabilities. If the chip is fully locked and you don't have any bug, this will not work. But let's say that we found something. Okay. In this case, this setting, because it's blind exploitation, it's not trivial. It's not your first exploit that you would write. And if we get an over-the-air update, this thing supports wireless. So if you update it wirelessly, for example, then you will break the exploit. Okay. So you have quite some caveats. So this is the moment that, if you remember the keynote that we had on yesterday from Herbert, I start to see that many talks go to this convergence of different domains, this synergy of attacks. So if we look at glitching and software exploiting, hardware and software attacks, performing, for example, a single glitch is very easy. This is something that you have seen with a stupid MOSFET, you can glitch things. Yeah, it's really like that. But multiple glitches, this is much more difficult because you're hammering the device, and if you hammer it too much, instead of it doing something interesting, it breaks. So if you want to multiple glitches, it's difficult, and this is especially so if the software running there is not time constant. You have moving targets. Exploiting several vulnerabilities in software is also very difficult. Chain exploits are not easy. But many simple, stupid exploits are easy. Okay, so maybe you can do just a single exploit, and then it's much easier. So we painted, as a summary, a very complex situation for software exploitation. Fully locked, blind exploitation, whatnot. What if we use what we know from all the talks and our experience from exploitation and from glitching, and what we do is the following. What if we change the scenario, we make our life easier by using a simple glitch, a stupid glitch, a simple exploit, rather not complicated exploit, and we combine both. Okay, so I like to think of it like a bit of this matrix, like some rules we can exploit and some others we can glitch. So this is a classical divide and conquer approach. We have a complicated thing, and then we can divide it in chunks, which by themselves they don't work, but the combination is much more powerful. So if we can divide a complex fault injection attack or a software attack into chunks, so that we can have a simple glitching attack and a simple software exploit scenario, we can achieve very powerful things. As an attacker, especially if you're doing software exploits, what does it mean? I have many challenges for software exploitation. Which one is the nastiest? what is the thing that is really bothering me? And if we have this thing that bothers me, can we glitch it? Can we modify it or alter it or remove it even by this glitching? We're going to see how it works. We have even a demo. In my backpack, maybe I can show you later, I have quite some boards that we glitched and we destroyed, so hopefully the demo code will be nice, but I don't know. A disclaimer before we show this. So this is an old disclaimer. We will see a combined FI attack on a specific microcontroller, but this is a general problem for general purpose microcontrollers from all vendors. Unless explicitly stated the chip is resilient or secured against security fault injection, you can assume that many of them, if not all of them, will be vulnerable to some extent. I put as many manufacturers as we can. All of them have one paper that shows an attack with fault injection. This is not new. 2015. This was in a CCC camp in summer. I was with Ramiro. We were explaining how it works there. I was taking pictures, showing this live. We said the same thing. 2018 here. Hardwear.io, one of my colleagues, Santiago Cordova, was explaining how fault injection works in automotive. We also put it there. So this is something that is known, and this is something you should be aware if you're making systems, that chips are glitchable. Back to our attack. Okay, so let's see how this divide and conquer attack approach works. And as I said, we want to see how can we abuse these glitching features for our software exploit attack. So if we look at all the restrictions we have, from a software point of view, the one that I find the worst is blind exploitation. I'm lazy, I want to see at least, I want to put some code and see what happens. So if we cannot load code or we cannot debug, what do? Well, we start glitching, and we will craft an attack. The stack steps are the following. First, we're going to glitch the chip and hopefully unlock it. Okay, so we will spam a single glitch, a simple attack, and see if this works. If this works, step 2, we can now load code and debug from the non-secure domain. So let's put there some exploit and see if we can now compromise the chip or the rest of the chip. Okay, so we will try to abuse this secure, non-secure interface, which seems the only gate from the non-secure domain, and see what happens. Okay, so now, any questions so far? No? Okay. Now, the settings. If you remember, a recap, we have this option byte that says the chip is unlocked or the chip is fully locked. Anything else is the chip has the debug enabled, but you cannot really read the code or do many things. So our plan, we're going to try to corrupt these configuration bytes, then we get into a partial lock, and then at least we can load code or do something with it. Okay? So this, how we're going to go about it. We're going to boot the chip many times. We're going to try to force loading these option bytes, see with a power measurement if we can spot where it is, and then glitch there. So this is how the chip looks. If you boot it from power off, then we get this over here. This is, well, the laser pointer you don't see, but where the arrow is, you see that there is a spike, and then we have a certain pattern. And if we just press the reset button, then that spike at the beginning doesn't happen and the chip boots faster. Actually, if you read the datasheet, it says the readout of the option bytes only happens from power off or when you force the reloading of it. So this pattern happens only when we power up and doesn't happen else. So this is our candidate for option bytes loading. Let's glitch there. So we tried. And then we start glitching there, like glitchy. Okay? In this case, we modify slightly the board. We remove the decoupling capacitors. Sometimes this is not needed. In this case, we did. And then we did some FI profiling rounds. And then we start glitching a lot. And we start even with really, I would say, crazy glitches, like dropping the voltage to -4 volts for 1 microsecond. You could see here, there is a spike there. Usually when you have glitches that big, either you have the device doing something or you have smoke. But this device was sort of, okay, what's going on? Well, what's going on is nothing. Interesting. So in this case, this chip has an internal power supply. It's called switching mode power supply. And that thing seems to eat glitches for breakfast. So, cool. As a developer, if you can, please use it. You can disable it if you want by software, but please use it. This thing makes voltage glitching a lot harder. But of course, we don't give up easily. So this doesn't work. This is the moment that when things don't work as you expect, you go back to the books and, okay, let's study further. Study further means datasheet. You start reading further, and then you see when the voltage supply drops below the selected brownout region, then this thing, this SMPS that you found, is actually bypassed. So basically, we don't have this. Now we just connect the input and output of this SMPS, so we bypass it. So what we did is, okay, cool. So let's lower the voltage to the minimum so that this happens. And what happens when we start glitching? Hey, we start getting glitches. Cool. Also, the datasheet says, if you do these connections and you do this, you physically bypass the SMPS, the switching mode power supply. So we did that and see what happens. What do you get? More glitches. For experimenting, this was just for fun, but what happens if we do EMFI, electromagnetic fault injection? Also glitches. Okay, so glitches is something that if you try a bit, you will always get. A simple glitch happens. And this is interesting because now, for this first step, as the attack results and the conclusion, basically, we have the datasheet saying, if you go to level 2, then this basically is irreversible and you cannot debug anything and whatnot. Might be there should be some asterisk that says except if you try F high, because then this is not irreversible anymore. So yeah, basically you can start opening JTAG, but this is, what can we do with this? Okay, so this is something that, well, it happened that we took this ST chip, but if we tried other vendors, we probably can do the same. So, yeah, what we can do is at least we can load code, we can even go to this fully debug mode, but we will erase the non-secure flash, the user data. The security domain is still intact, that thing is untouchable, okay, but we cannot do anything. So in this case, what we will do is, okay, at least now I can load code. My first stage, my first limitation that I cannot do anything with a glitch, now we bypassed it. So what next? Well, now this is the moment that we will go to a software exploit. Okay? So in this case, I'm going to give the word to Federico.
Okay, thank you, Rafa. So indeed, now we are in a situation where we can control all the code that is being run in the non-secure core, and we want to try to attack the secure core. And the way the communication works between the two cores is very simple. It has a mailbox system called IPCC. It's the usual mailbox system. You set a bit in a register, you trigger an interrupt on the other side, and then the other side can start parsing the command. And there is a shared buffer between the two cores in SRAM, and the offset within this SRAM memory is set in one of the option bytes. Now, the messages within this command buffer are not just simple command response, but actually they are quite complex messages. They have pointers to pointers, etc. And the secure core will have to parse them, process them, and write them, their answer back to the same shared memory. One thing important to notice is also that there are many different firmwares you can load in your secure code core, depending on the functionality you want to implement. For instance, you can load a Zigbee firmware, or you can load a Bluetooth firmware, but the flash update firmware, which is used to update the firmware of M0, is always present. So we decided to focus on this specific firmware. And ST documentation is very open about this, and it contains a lot of information on how to talk to the secure firmware. And the first thing you need to do to talk to it is set up this table, where each of these entries is a pointer to another table. And for our attack, we would like to focus on the system table that is the main one used to communicate with the firmware update service. It's the fourth entry here, as highlighted by the arrow. Now, if we look at ST's documentation, we see that within this system table, there is at offset 0 another pointer to a buffer, and this is our command buffer. We will put our command there, and the secure core will put its answer back in the same location. So fortunately, we don't have to set up all these tables ourselves, because the ROM code implements some functionality to update the firmware in the secure core, which means we can simply connect the JTAG. As we mentioned earlier, JTAG access is open. We can read out the ROM. We can also read out these SRAM tables. which have been set up by their own code. So we don't have to compute them ourselves. And this is how they look like. I hope everybody can read them. Maybe they're a bit small, but I'll try to go through them. This is the beginning of a shared SRAM. And if you remember earlier, I said we will focus on the system table, which is the fourth pointer. And you can see there, it's highlighted there, 1, 2, 3, 4. Now, the base address of SRAM is 20.03.00.00, and this is in Little Endian. So basically what this says is that it will point to the next table, which is at offset 5C within this view. And there's offset 5C. And here is exactly the same thing. There is another pointer to offset 64. Where is offset 64? There. So that's where we will have to put our command, and that's where the secure core will put its answer. So there are 2 pointers to be dereferenced. Is it done right? And of course, if I ask the question, you probably guess the answer. But what should the secure core check? It should check that both buffers should be fully within the shared SRAM, and it should check this both when reading from the buffers and when writing back its answer. So we started thinking, let's try to do a sort of time of check, time of use attack. We set up a correct table, we already have it there. We send a command, put it in the buffer as it was shown, and then we wait some time for the secure core to be able to read this command, and then we change the tables to point the response buffer somewhere else. So we hope that the secure core will read our message from the shared SRAM, but because we change the pointers in the meanwhile, it will write its answer in internal memory. Hope that something nice for us happens and we can get something out of it. This step is still a bit unclear at the moment. And we tried the approach, and indeed it seemed to work. So, for instance, we could point this shared buffer after sending our command to a physical address that does not exist. Nothing is mapped there. The secure core will crash. And this gives us indication it was trying to write to a map memory. So, what do we want to override now, and with what? This is not very simple, because the set of answers that the secure core can return is very limited. It's always 5 bytes that it will write back. 2 bytes are fixed header we do not control at all, an acknowledgement of the command ID that we fully control, and 1 status byte that says whether the processing was successful or not. So it's usually either 0 or FF. We do not have access to the firmware running on the secure core. The secure core is also configured so that only the flash is executable. We cannot somehow corrupt the value on the stack and have it jump to our code. This is a very difficult primitive to use blindly. So since we couldn't come up with anything smart, we decided to try something simple. If you remember earlier, Rafa explained that there are some secure option bytes that define the security of a secure core. So these option bytes are memory mapped. We know where they are mapped because the view of the physical address is the same between the 2 cores. And we decided, let's maybe just point the response buffer on top of these option bytes. See what happens. To make things even more unpredictable, because these are 32-bit register, but the answer is copied byte-wise with a mem copy that does it byte-wise. It will not actually write there what you think it's going to write there, because if you write 8 bits into a 30-bit register and offset within these registers, the hardware might do strange things depending on how the register is implemented. So let's say, let's just try to point it there. Let's try to be lucky. What do we need to be lucky? Well, if we look at the documentation of ST, there are actually a lot of ways to completely disable the security there just by simply flipping 1 bit. So there is this, which disables CPU2. CPU2 is another name for the secure core, or M0. Debug access. So if we set that to 0, for instance, we will enable JTAG access to the CPU2. We can completely disable flash security, so the whole flash will be accessed to the non-secure core. You can modify the start address of a secure flash. You can also change the reset vector of the secure core, which means even though there is a configured secure flash, you can make the reset vector point to non-secure flash and have a secure core boot from there, which we can control. So we decided, whatever, let's not think about it. Let's just run the attack, slam something on top of the secure option bytes and see what happens. And actually we were successful. So we managed to get lucky. And by pointing the answer on top of the secure option byte that configures the start address, so the reset vector of M0, this reset vector will point to non-secure flash. And we can simply control the contents of a non-secure flash. We can program there some small shellcode that disable all the security, enables JTAG, etc. And then we can read the full secure flash, both from non-secure core and the flash, and the JTAG. So, for a full attack, what do we need to do? Well, we would simply need to get a device, just from the shelf, fully locked one, use fault injection to downgrade the security. That's what Rafa just presented. We can erase the non-secure flash only and go to unlocked mode and load our software exploit. And then we can also compromise the secure core and run our code from there. And yeah, maybe something interesting to notice is that earlier we mentioned secure core has some secure key storage, and these keys are hidden from the non-secure core. But because of this attack, even though we erase the non-secure flash, the secure flash is still preserved, which means we would lose any key that is stored in the non-secure flash, but we can recover all the keys that are stored in the secure flash, which is sort of counterintuitive if you think about it. Anyway, now it's demo time, and Rafa believes in the demo gods, so he can do the demo.
I will try my best. Let's see. So, one of the things that I should mention is, well, I can show you later a stack of boards. Actually, I got only this board yesterday, so we cannot really reproduce all the steps because I cannot now be fiddling with setting the jumpers, and this is a bit shaky, but at least hopefully the glitching part I can show. Okay, so let's minimize all these things. Minimize more. So what happens is the following. Here I have now the device, and the device is fully locked. And what we did is we connected the power supply to this device, which allows now to inject glitches. And basically what's going to happen is we power off the device, power it up, wait for some time, and this time that we found this where the option byte is, glitch, glitch, glitch. Okay, so a very naive approach. Then here, hopefully you can see my screen. Yes, you can. So we did some initial campaign to try, and then here we have different settings that we were finding this seems to work in our case. Okay, and in around that timing over there, that time window is where we guess that this is happening. So now demo gods, please don't fail me too hard. We start this. Okay. My computer is thinking about life. Okay, come on. Yeah, I think there were too many successful demos in the previous one, so now we have a bit of bad karma. Come on. Is this on? Yes, this is. Did I click on the wrong button? Maybe. Okay, I think I might have clicked on the wrong button, so let me try once more. And yeah, as I said, connecting things now. Okay. And let me quickly check one more thing. Okay, the demo effect. Yeah, this is, I guess, the coffee time is now just pressing. So, well, then I'm going to do one thing. I'm going to restart the tool just because the solution of IT for everything often works, which is just power off and power up everything. Okay, so I have this is reset, this is done. Let's restart the software. In the meantime, now I can explain what's going to happen. So basically here we had an application which is telling us the option bytes, and then you will see that we're going to try glitch, and hopefully we will manage to trigger that this option byte that is the lockdown glitch, the lockdown option byte, we will glitch it back to something random, because this is basically this mode where we have partial access. And if we get to do that, then we should see something. Okay, so let me also disconnect this just in case. The demo effect. Yeah, I don't have any good joke to tell now. So, okay. So,
do you want to take some questions while we're waiting?
Yeah, if you have any question, we can take one question in the meantime. Yes?
Okay, thank you very much for your presentation. Glitches are very efficient, but they are also very dangerous. I don't know if you encountered any memory erase or you already damaged the chip while you are doing this kind of glitch for the moment.
Sorry, I could not hear correctly the question.
Well, my question is just, did you encounter any memory erase while you are doing the glitch during the boot of the chip?
So is the question, did we encounter any memory range?
Erase.
Erase.
Yes.
Yeah, it's a good question. So the default firmware, so when you get the chip from stock, what we found is sometimes we corrupted these option bytes, and then we didn't erase the flash, but we corrupted these option bytes in a place that it got bricked. The newer update of the firmware actually prevents this from happening, because glitches also happen in nature. Physical destruction of the chip, it was really hard, so we did not actually erase the flash. We just corrupted things.
Okay. And what you can do to achieve the attack if you already corrupted the option bytes?
In this case, if we corrupt the option bytes, then we can later now go back to this partial locked status, and then we can have some access. We can just start debugging and doing something from there, which was from blind exploitation to something. That's a change. Okay. So unfortunately, I don't know what's going on, but yeah, thanks for the question. So I don't know what's going on. So what I'm going to do is I'm going to just wrap up the presentation so that you can see what happens. But later, if you want, we can show this in the coffee break, or you can see it. So basically, I have this in just in case the demo was failed. So we have, this is what happens, that then you read, the readout protection byte can be 0, 1, or 2, or A, B, 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 or C, C, but then we get FF. Then we can go back to this AA. This would trigger a flash erase, but then when you connect the debugger, you have several options. And for example, this DDS, this debuggable service of this secure core, now it will not be there. Okay, so this is something that we don't do with FI. This part we would do by, one second again. We would do by doing a very simple exploit, which is basically what Federico explained. We wrote a payload in the non-secure area. Then we would just first try to corrupt the secured core its own configuration. So we corrupt the start address. And then we will make this program to run again, but instead of corrupting the option bytes, what we would do is we would just store them. We would just store them with an option which says unprotect everything. Okay, so first FI, then once we have access to the chip, we would run this exploit in software, which is, 10 lines, 20 lines, not very big. And then we would manage to get control. Okay, so everybody's is with attention and silence. This is also very scary as a presenter. Okay, so conclusions, wrapping up. Though, basically, with this divide and conquer approach, as you can see, we didn't try anything sophisticated. This was just a simple glitch, and this was just a simple exploit, not super complicated. And what we did is basically glitch this readout protection mechanism. We have now access to secure, non-secure domain. Then we found an exploit. We just wrote so we found a vulnerability. We wrote a simple exploit, and as a result, we achieved a full compromise of the security domain. Okay. Something that we didn't get due to our simple approach is that our strategy erases the non-secure domain. Okay, so we delete the data there, and as Federico explained, if you put secrets there, it's counterintuitive, but actually this would be deleted. It might be possible to avoid this downgrade step. We didn't try. Okay, this is just for you to see that simple glitch, simple exploit, powerful attack. Mitigations. So as a developer, this is important to know. You have not just the pure software exploits. FI, if you consider as a software exploitation primitive, is actually quite powerful. And this was very naive. So this was just my first glitch day attack. So this is, for example, I don't know how to call it, multi-entry-level attacker, multi-noob attack. This is not considered in threat models. You have entry-level attacker or expert. What happens if you have a couple naive attacks and then suddenly it's like multi-expert level? Okay, so this is interesting to think. As a first step, including FI as a threat model in your threat model is useful. Second thing, if you use this specific chip, please use the switching mode power supply. This thing eats glitches for breakfast, so it's actually quite nice for developers. And also it's useful to add secrets, add barriers in every single part. Our attack, if you had some secret also in this non-secure area, this would have been blocked. Finally, software updates. So this is something that at least the software exploit can be patched by an update. And actually this was patched, so this we did coordinated disclosure to ST, and they patched it in the version 1.10.1 of the firmware. Okay, so here, this is just, we did coordinated disclosure. There is some dates, later you can check the slides. But basically it's nice to see that developers sometimes care about security and they actually patch things. And well, in the end, we all use these devices, so at least it makes me happy that things are getting better. As a conclusion, from an attacker point of view, then dividing complex exploits into simple attacks, it might look difficult, like hardware or software, but actually we are using simple things. This is like my first exploit, my first glitch. And as a result, the result is much more powerful than the individual things. Okay? So in this case, a simple FI attack, maybe to learn, is that it can change completely the software exploiting scenario. And fault injection resilience is just hard to implement it right. Okay, so if you see a datasheet and there's no FI protection, divide and conquer, glitch something, and just make your life easier. And yeah, these kind of techniques you will see more and more often in the InfoSec news, that glitches are there. You saw that most of the talks this year on hardwear.io had something to do with glitching. Well, not most, but a lot of them. So something that happens. If you're a developer, then be aware. This is something that is happening more and more. If you put barriers, then it's better. How to do that? Include FI in your threat model. Think that people can try stupid glitches. Patch the firmware. Okay, so this will mitigate at least the impact of FI. Also, use the security features and properties of the platform. So you saw the presentation from Dr. Sergei Skoroborakatov. We have security features not used. If you have it there, use it. It's useful. And also, it's important to put secrets scattered, because then it makes it more difficult. The attacker needs to now succeed in all fronts instead of one, and then you have all the eggs in the same basket. So this is the end of the presentation.
Thank you. And yeah, I'm sorry your demo didn't work. Next time I recommend you satisfy a unicorn before you start, and then they always work. So we have a long coffee break, so we actually have another 15 minutes. So if anyone has a really burning question.
So I think I might have just missed this. The software that was actually handling the mailbox interface, were you saying that was a firmware update firmware on the M0 side? And then you listed there were like multiple other potential things. Did each of those other things use a similar sort of mailbox interface from the M0 to the M4?
So yes, they do. and we didn't really look in depth on whether they have similar vulnerabilities. I quickly tried with one firmware, I think it was a Bluetooth, and it was at least not vulnerable to exactly the same attack, but it's not something we researched thoroughly.
Okay, that was going to be one question, is whether you checked the others. The other question was, you were treating the M0 like it was a complete black box and that you had no visibility whatsoever into it. Do you know whether that firmware update or firmware component was used in like reference implementations for STM? Like basically if you had bought like a developer's board, would you have seen that same firmware there, and therefore you could have just, made some assumptions about, well, this is what ST uses over here, so maybe it'll be on this other system that I want to exploit?
So actually this firmware has to be there. ST makes it and they sign it, so they are the only people that can load code into the M0. And if you don't have this firmware updated service running, it means you will never be able to update the firmware of the M0 again. So my understanding is that this M0 will always be there. This firmware update service will always be there on the M0. Maybe different versions, but it has to be there.
Thank you.
Since all of the M0s are running the same firmware, that means that there is a secret key in the chip itself. Were you able to extract that or dig through the firmware to try to figure out where that decryption is done?
We would never do that. But yes.
Okay, but when somebody extracts it, it's a class break against all of these chips.
Yes. There is, of course, also a public key to verify the signature of the firmware. So that still protects something.
So thank you very much.